NCTS annual meeting on particle cosmology and strings. This is the third conference of this conference series. Thank you for coming this early. I think more people are still on the way, so we'll have more people. And for those coming so early, and some of our guests from abroad also coming this early. Thank you. So we'll go according to the program schedule. Let us first welcome Director Chang-Xin Zhu for NCTS to give a welcome speech. Let's welcome him.
Good morning, dear distinguished guests and my dear colleagues from the whole community. It's early in the morning, so I would expect more people, but anyway. Yeah, very welcome to Hsinchu and NCTS. As Xiaowang just mentioned, the annual meeting started about 3 years ago. The meeting consists of two parts, one on condensed matter physics and one in particle cosmology and fundamental physics, string theory. This is the second part. So the meeting is supposed to be of an interdisciplinary nature. Third one, yeah. Sorry. Of an interdisciplinary nature, because we find ourselves very often we are focused in research and maybe we lack a complete picture. In particularly for students, this is often the case. So we organize this meeting in order to hope to break the barrier. And this is your job in the next few days. For those of you who are going to make a presentation, we are looking forward to hear about the advances in respective field in your research area. So when I look at the program, I find very many interesting topics, ranging from neutrinos, colliders, Euler-Center model, symmetry breaking, black hole, non-perturbative phenomena, holography, gravitational wave, vacuum of string theory, and many very interesting topics with a lot of progress made this year. So I'm sure the meeting will be very stimulating, and I hope you will enjoy it. And so with this, I sincerely thank you for all of you for your contribution, and best wishes for a successful meeting.
Well, thank you, Dr. Zhu. He saved us some time, but that doesn't mean the speakers can extend it too much, right? Okay, so we'll come to the scientific session. The first talk will be given by Professor Eric Braaten on zero-range effect field theory for WIMP dark matter. Let's welcome him.
Okay, well, as announced, I would like to talk about zero-range effective field theory for resonant WIMP dark matter. This is work I've done with a student at Ohio State, Evan Johnson, and with a postdoc, Hong Zhang, who's now at the Technical University of Munich. And we're grateful for the support from the U.S. Department of Energy, and I'm especially appreciative to the organizers of this conference for having invited me to speak here. This talk is based on 3 papers that we've written that are entitled Zero-Range Effective Field Theory for Resonant We Know Dark Matter. The 3 papers are subtitled Framework, Coulomb Resummation, and Annihilation Effects. And the last one has not yet appeared on the archive, but should be there shortly. A WIMP is, of course, a weakly interacting massive particle. And by massive, I mean mass larger than the larger or comparable to the weak scale, which is about 100 GeV. By weakly interacting, I mean having ordinary SU2 weak interactions with coupling constant alpha 2, which is 1 over 29.5. The exchange of a W or Z gives you a WIMP-WIMP scattering cross-section that's of order alpha 2 squared over MW squared. And a WIMP pair can also annihilate into electroweak gauge bosons with an annihilation rate proportional alpha 2 squared over the WIMP mass squared. A neutral WIMP is, of course, a candidate for the dark matter particle because it naturally has a thermal relic abundance that's comparable to the observed dark matter density. WIMPs can have non-perturbative weak interactions, as first pointed out by Hisano, Matsumoto, and Nojiri in 2002. That is, loop diagrams can produce factors of alpha 2 times the WIMP mass divided by the W mass. And that mass ratio can compensate for the small coupling constant. If the WIMP mass is comparable or larger than the W mass divided by alpha 2, that is 30 times the W mass, that is around a few TeV, then the ladder diagrams must be summed to all orders. In the case of the annihilation, the effect on the annihilation rate is commonly referred to as a Sommerfeld enhancement, whether or not it has anything to do with the physics that Sommerfeld studied way back 100 years ago. The effects of these non-perturbative weak interactions can be conveniently calculated using a non-relativistic effective field theory for the WIMPs that was pioneered by Hisano, Matsumoto, and Nojiri. It's an effective field theory for WIMPs with a momentum much less than the mass, and therefore velocity small compared to the speed of light. The weak interactions of WIMPs in this effective field theory are described by instantaneous, non-local potentials that come from the exchange of W and Z. Using the Schrodinger equation, you can solve numerically for results from the 2-WIMP problem and get WIMP cross-sections, WIMP pair bound states, WIMP pair annihilation rates, and specifically the Sommerfeld enhancement. Now, WIMPs can also have resonant weak interactions, and by that I mean that if the mass of the WIMP is large enough, the attractive weak interaction can produce bound states of WIMP pairs. And if you're near the critical mass for producing a bound state, these cross-sections and annihilation rates can be enhanced by orders of magnitude. The most dramatic enhancements occur in the S-wave channel. And that's because if the S-wave resonance is exactly at the threshold, the elastic cross-section will saturate the unitarity bound for a significant range of velocities, ranging roughly from alpha 2 squared, which is 10 to the minus 4, to alpha 2, which is 0.03. And we can get enhancement factors as large as 1 over alpha 2 to the 4th, which is 10 to the 6th from the effect of the resonance. And so this is what I want to discuss, the effective field theory that will describe these resonant interactions. This slide shows you the WIMP elastic cross-section as a function of mass and the WIMP pair annihilation rate as a function of mass for a specific dark matter model. This happens to be for Winos. But you'll see that when the first S-wave bound state appears, you get a huge enhancement of the elastic cross-section and a huge enhancement of the WIMP pair annihilation rate. Beyond the bound state, the rate goes down, but then there's a second S-wave bound state that comes in, and again, there's a huge enhancement in both the cross-section and the annihilation rate. So the zero-range effective field theory that I have been advertising is one that describes the WIMPs in this region of mass. It describes WIMPs with an S-wave resonance near the threshold, such that the scattering length of the WIMPs is large compared to the range of weak interactions. And that allows you to describe the weak interactions of the WIMPs as local interactions, where the WIMPs interact at a point. And of course, it's a non-relativistic approximation, and the momentum must be small enough so that you do not resolve the weak interactions. So momentum is smaller than the W mass. And with this, we can get analytic results for the 2-WIMP problem: the cross-sections, WIMP pair bound states, and the WIMP pair annihilation rates. In addition to analytic results for the 2-WIMP problem, this could be useful for several other reasons. One is that it simplifies the numerical solution of the 3-WIMP problem. One problem that would be particularly interesting is 3-body recombination, where the collision of 3 WIMPs produces a bound state and a WIMP. And to explore the effect of dark matter, it would be useful to calculate the 3-body recombination rate. And finally, one other possible application is as a rather predictive model for strongly interacting dark matter, in which case you need a much smaller dark matter mass of about 15 GeV. This can explain some of the anomalies for the large-scale structure of the universe. Small-scale structure of the universe. Okay, so I hope this gives you some idea of what I mean by this zero-range effective field theory. It's a field theory for non-relativistic WIMPs. I'll describe the possible field theories can be used. And then I'll take a detour to discuss systematically improvable effective field theories and how they apply to this problem. Then I'll go through the zero-range effective field theory, describe what's in these 3 papers on the framework, the Coulomb summation, and annihilation effects, and finally give you some results from this effective field theory, and then conclude. Okay, so I'll begin by explaining what I mean by we know dark matter, because I'll be applying this effective field theory specifically to Winos. What I have in mind is the minimal supersymmetric standard model in the corner of parameter space where the neutral Wino is the lightest supersymmetric partner, and the only nearby SUSY partners are the charged Winos. Or it could just as well be the standard model with one additional SU2 multiplet having the neutral and charged Winos. The neutral Wino mass, I want it to be at the TeV scale, so the weak interactions are non-perturbative, and I'll take this mass to be an adjustment parameter. The charged Winos will have a slightly larger mass, by number delta. This mass splitting is given by electroweak radiant diffractions, and it's very insensitive to the Wino mass, and I'll keep it fixed at 170 MeV. And finally, Winos, the important interactions of Winos are the local couplings to electroweak gauge bosons, the photon, the W, and the Z. There's many momentum scales involved in Wino dark matter, and they range over more than 5 orders of magnitude. First of all, there's the Wino mass, which might be 2 TeV. There's the weak boson masses. The W mass is 80 GeV. There's a non-perturbative weak scale. Alpha 2 times m is also 80 GeV. Then there's the Bohr momentum, which is alpha times m. This is the momentum associated with Coulomb bound states, with charged Winos. This is 20 GeV. There's a scale that comes from neutral to charged transitions. This determined by the splitting delta. This is 30 GeV. And finally, if you have an S-wave resonance near threshold, there's another scale that can be orders of magnitude smaller. This is the inverse scattering length, which can be as small, whose absolute value can be as small as MW times alpha 2 squared. That is 100 MeV. So there's a huge range, there's many momentum scales and a huge range of them. But if you're dealing with non-perturbative Winos, you don't have to describe them all explicitly. The fundamental theory does describe all these scales explicitly, but this non-relative effective field theory does not describe the Wino mass scale explicitly. It integrates that out. And this zero-range effective field theory does not describe the weak boson mass scale or the non-perturbative weak scale explicitly. It only describes explicitly these small momentum scales. The weak interactions of Winos in the fundamental field theory are given by local couplings to WZ, and they come from exchange of WZ. In NREFT, they are described by instantaneous non-local potential from exchange of WZ. In ZREFT, the interactions between Winos are local. Weak interactions are interactions at a point that will reproduce the effects of the weak interactions in the fundamental theory. Once again, I'll describe briefly this non-relativistic effective field theory for Winos that is introduced by Hisano, Matsumoto, and Ujiri. There's the particles are the neutral Wino and the charged Wino, which have the same kinetic mass, but different rest energies. The charged Winos have a larger rest energy by 170 MeV. The two-body problem has 2 coupled S-wave scattering channels for the neutral Winos and the charged Winos. And the electroweak interactions can be described by a 2x2 potential matrix. There's a long-range Coulomb potential, alpha over R, that involves only the charged Winos. And then there's a weak potential matrix that's a 2x2 matrix whose off-diagonal elements are couplings between the channels. if you solve the Schrodinger equation numerically with this 2x2 matrix potential, you can calculate the WIMP cross-sections and the WIMP pair bound states. But there's also annihilation of neutrino pairs into pairs of the electroweak bosons, 2 photons, W plus W minus, etc. And to take that into account, you need to add an imaginary zero-range annihilation potential that will reproduce the effects of annihilation. If you also add this delta function potential, then you can not only calculate the WIMP cross-section, the WIMP pair bound states, but also WIMP pair annihilation rates. And what I want to describe is an effective field theory that is explicitly applies when there's a S-wave resonance near threshold. And I would like to take a diversion into describing how you use effective field theories to provide systematically improvable approximations. And because this will play an important role in the zero range effective field theory. What you need is, first of all, a renormalization group fixed point. One that is a fixed point describes scale invariant physics. Once you have this fixed point, you can find the scaling perturbations, which will be operators with increasing scaling dimensions. Then the effective field theory leading order includes all the relevant and marginal operators. And you get systematic improvements by keeping the irrelevant operators at next leading order, those with the lowest scaling dimension, at next to next leading order, those with the next lowest, etc. Now, in most applications of effective field theory, this RG fixed point is just the usual non-interacting fixed point, but it also can be a non-trivial interacting fixed point. And this is what happens in this case of the zero-range effective field theory. Let me begin by considering the field theory for non-relativistic particles with one S-wave scattering channel. The energy of the particle is p squared over 2m. This is scale invariant. Energy scales like a power of p, and there's no momentum scale that affects the p dependence. In the two-body problem, the S-wave scattering is described by a T matrix that is determined by the S-wave phase shift. As an aside, if you have short-range interactions, this T matrix has a low energy expansion in powers of the energy or equivalently k squared. The first term of this expansion is conventionally denoted by minus 1 over a, where a is the scattering length, and the second term, the coefficient is the effective range of, which I'll be using later. But you can easily imagine, there's one fixed ultraviolet fixed point that's scale invariant that you can easily see, and that's simply the non-interacting fixed point, where there's no scattering. That certainly is a scale invariant, But there's also a non-trivial fixed point, called the unitarity fixed point. You can describe the fixed points by setting up the renormalization group framework with ultraviolet cutoffs and all that. But you can understand it much more simply just by describing it in terms of physical observables. If the T matrix element is just 1 over k, then the S-wave, scattering amplitudes saturate the unitarity bound. Unitarity bound is that the cross-section is 4 pi m divided by e. And this is scales like a power of energy, and there's no scale that affects the interactions. So this scattering that saturates unitarity bound is scale invariant, and that is what the unitarity fixed point is describing. Let's go to the problem with two S-wave scattering channels. In our case, we have two particles, the neutralino and the chargedino, with different energy thresholds. And you can easily see that unless delta equals 0, there is a scale given by the energy momentum relations. So scale invariance requires that the splitting be 0. The S-wave scattering channels for neutralinos and chargedinos are coupled, and so they'll be described by a 2x2 T matrix. And the question is, what are the possible fixed points for this T matrix? Well, first of all, we know that the splitting should be 0 at the fixed point. You also need to turn off electromagnetism because the Bohr momentum provides a scale. And after you do that, you it's obvious there's one obvious fixed point, namely t equals 0, no scattering whatsoever. That's scale invariant. There's also another quite obvious fixed point, and that's where the scattering length in both channels saturates unitarity bound. And when we started this problem, we tried to, we wrote down a simple effective field theory with neutral, that described neutral winos and charged winos, and with point interactions for the weak interactions, and tried to reproduce the results of the non-relativistic effective field theory from solving the Schrodinger equation. And we found it to be much more difficult than expected. We could not get the shapes easily, and we could not get the accuracy that we expected in describing the NREFT results. And it turned out that the reason for this is that we were implicitly working around this two-channel unitarity fixed point. And when the fixed point like this actually implicitly assumes that you have done fine-tuning of two parameters in order to get two resonances near threshold. In our case, we were adjusting the Wino mass. That's one parameter. And that can fine-tune one bound state to near threshold. But this implicitly assumes two bound states near the threshold. And the correct fixed point was actually discovered a while back in 2011 by Lenski and Bierce. They were analyzing a nuclear physics problem involving scattering of lithium-7 plus proton plus beryllium-7 plus neutron. And what they noticed that there is another scale invariant fixed point in which the scattering saturated unitary bound in a specific resonance channel, which is some linear combination of the neutral and charged winos, and there's no scattering in the orthogonal channel. So this is the single channel unitarity fixed point. And what we needed to be doing is to be working around this fixed point. And once we realized this, then things fell into place. Lenski and Bierce analyzed the scaling perturbations about the single channel unitarity fixed point. There are two relevant operators. One gives you the mass splitting between the two channels, delta. Another gives you the scattering length in the resonance channel. There's a single marginal perturbation that corresponds to varying the mixing angle phi. And then there's irrelevant perturbations that correspond to the scattering length in the orthogonal channel, the effective range in the resonance channel, and so on. And to describe, the effective field theory leading order requires including all the relevant and marginal operators, namely kinematic parameters are the mass of the Wino and the splitting. Interaction parameters are the scattering length in the resonance channel and the mixing angle. At the next leading order, you have two additional interaction parameters that correspond to these first two irrelevant operators. So now I can describe what's in those three papers that I was advertising. In the framework paper, we turned off electromagnetism, alpha was set to 0, and the bubble diagrams from these weak interactions that were represented by point interactions. This can be done by solving Lipp and Schwinger equations. At leading order, there are two interaction parameters, and we found that we got good predictions because we could reproduce the results of NREFT for the Wino-Wino cross sections, except that charged Wino elastic scattering was not well reproduced. If we went to next leading order, added two additional interaction parameters, we got improved predictions for all the Wino-Wino cross sections, which indicated that we do have a systematically improvable framework. In the second paper, we turned electromagnetism on, set alpha to 1 over 137. In this case, you have to sum the bubble diagrams, but within those bubble diagrams, you also have to sum ladder diagrams with photons to all orders. This was actually done way back in 1999 by Common and Ravndahl in developing an effective field theory for proton-antiproton scattering. So we could take advantage of their analytic results for these resummations. So the ZREFT at leading order, the interaction parameters are alpha, 1 over 137, plus two real interaction parameters. And they give good predictions for the Wino cross sections. In the third paper, we turned on the annihilation effects of the gauge boson pairs. In a local effective field theory, this can be done simply by analytically continuing the real parameters in Lagrangian to complex values. The zero range effective field theory at a leading order, interaction parameters are alpha is 1 over 137, and two complex interaction parameters that have small imaginary parts. In this case, we got good predictions for the Wiener-Wiener cross-section, the Wiener-pair annihilation, and the Wiener-pair annihilation rates. That is, they reproduce the result of the non-relativistic effective field theory. Let me give you a few more details on the ZREFT. At leading order, interaction parameters are alpha, a scattering length, and a mixing angle, and these two are complex parameters. We determine the parameters by matching with a non-relativistic effective field theory, where you can solve for observables by solving the Schrodinger equation numerically. And we determine these two complex parameters as functions of mass with a fixed splitting 170 MeV. And the W0, well, the two most convenient variables to determine the matching turned out to be the inverse scattering length for neutralinos and the effective range for neutralinos. They both have real and imaginary parts, with imaginary parts much tinier than the real parts. So here's the real imaginary parts of gamma 0, here's the real imaginary parts of effective range, and from them we determine A sub u and phi. And once we have that, we can predict all these other observables. The first unitary mass is 2.39 MeV, where there's a huge enhancement in the cross-section. The effective range, the inverse scattering length at that mass has a zero imaginary part, which is why there's a huge peak in the cross-section, and a much smaller, well, a zero real part and a small imaginary part. This down here, you cannot see the tangent of the mixing angle, but it's 0.88 plus a number that's imaginary part that's 10 to the minus 4, 4 orders of magnitude smaller. It tells you that the appropriate mixing angle is roughly 40 degrees. Okay, once we have the matching addition that determine the two parameters, we can calculate other things. Here I'm showing you the neutralino elastic cross-section at zero energy as a function of the mass. These are, in fact, exactly reproduced by the zero-range effective field theory, just by having chosen real part of gamma 0 as one of the matching conditions. Another observable is the neutralino annihilation rate at zero energy as a function of the mass. This is, again, exact by choice of matching conditions that include imaginary part of gamma 0. But there are also non-trivial, well, there are other predictions that are accurate but not exact. This is showing you the elastic cross-section at the critical mass, where you have the huge peaks in the cross-section, as a function of the energy. And so here's the cross-section as a function of energy on a linear scale, and the cross-section grows dramatically as you lower the energy. This is the same cross-section on the log-log scale. Well, first, if you look at this cross-section, you see that the cross-section is huge at low energies, and then there's dramatic oscillations right at the charged Wiener-pair threshold. This just comes from the Coulomb interactions. These are Coulomb resonances that, just below the threshold. And what you can see, if you look carefully, there are two lines here. And it's not a perfect agreement, but the zero range, the red line, the thicker red line is the non-relativistic effective field theory numerical. The narrower black line is the zero range effective field theory. And you can see that although it's not perfect, there's a pretty good matching between the two results. This shows you that as you go to lower energy, you cannot see the difference between the NREFT and the ZREFT. The lower diagrams show the same thing for the neutralino annihilation rate at the critical mass as a function of the energy. This is a log versus linear scale, and this is a log versus log scale. At very low energies, the cross-section grows dramatically, but there's a very good reading to get into. Again, there's Coulomb resonances right at the threshold, and although the agreement is not perfect, there's a pretty good matching for this dramatic energy tank behavior by the effective field theory, by the ZREFT. One last thing I would like to one last thing I'd like to describe is the is the Sommerfeld enhancement factor. I'll consider this for the inclusive annihilation rate of two neutrinos. At leading order, the two neutrinos annihilate into W plus W minus, and with a cross annihilation rate, it's alpha 2 squared over m squared. The Sommerfeld enhancement factor is the enhancement in that annihilation rate because of the resonance. And what I want to point out is that it's completely an analytic expression for those of you like me who like analytic results. The only non-trivial function in here in this expression is this function k1 of e that appears in the numerator and the denominator. It's this function involves the Pauli logarithm function psi, and with a variable that is determined by the velocity of the WIMPs. And this is comparing the NREFT with ZREFT. You can see that there's very good agreement at low velocities, and there's slight, if you come up very close, you can see there's a slight discrepancy in large velocity, but the dramatic behavior here at the Chartavino threshold is reproduced. Okay, so let me just summarize. I introduced a zero-range effective field theory for resonant Wino dark matter. It's a systematically improvable effective field theory that's based on the single-channel unitarity fixed point, where there's the appropriate fixed point if you have a single parameter that's tuned to get to give you the resonance. At leading order, the ZREFT has 3 interaction parameters: the Coulomb interaction, alpha is 1 over 137, and 2 additional parameters. The most convenient matching variables we found were the inverse neutrino scattering length and the effective range. We obtained analytic predictions for the WIMP cross sections, WIMP pair of bound states, and WIMP pair annihilation rates. These results are analytic. In the previous work on Sommerfeld enhancements, there haven't been there have been toy models in which analytic results for Sommerfeld enhancements were obtained, but in realistic models there were no analytic results. Our results give unitarization of the WIMP pair annihilation rate. In most previous calculations of Sommerfeld enhancement, they were only to leading order in the annihilation interaction. If we could improve upon our results by going to ZREFT and NLO, and this will give you 2 additional interaction parameters. These analytic results for the 2 WIMP problems could be useful for exploring the effects of resonances, well, specifically S-wave resonances, on the effects of dark matter. It's more convenient than using the numerical results from NREFT because of the large dynamical range of 5 orders of magnitude of the momentum scales. It's not easy to do the numerics for NREFT. This approach can simplify the numerical solution of the 3 WIMP problem. A particularly interesting application would be to 3 recombination, where the collision of 3 WIMPs produces a WIMP bound state, and this can have some effects in the early universe. This ZREFT also provides a predictive model for strongly interacting dark matter. In this case, you have to take the dark matter mass to be about 15 GeV in order to solve some of the small scale structure problems of cosmology. Other dark matter applications would be of interest is resonant Higgs zenos, in which you have to solve there's 3 coupled channels that you have to worry about. And finally, this effective field theory also has other high energy physics applications, and one that's of deep interest to me is that of charm mesons and the X3872 resonance. So with that, I thank you for your attention.
Okay, thank you. Welcome. Okay, question? Yeah, okay.
As we know, the ZRFT is applied in the very low energy region. Do you have ideas to include the range? I mean the finite range.
The range.
Can it be treated by NREFT?
Yes, the range, when you add at next leading order, one of the two parameters that enters that next leading order is the range in the resonant channel. So as you add as you add irrelevant operators, range effects come in. And but still, the application is limited to momenta less than W mass, but that still corresponds to velocities as large as 10 to the -3. So it's not so necessary, at least for dark matter applications, to extend the range of validity beyond a velocity of 10 to the -3.
Oh, okay. But maybe go first one before others. First.
So there has been calculations, step improved calculations on we know annihilation.
Yes.
So I'm just wondering, so what is your calculation in comparison with that?
Okay, there have been calculations of the annihilation rate of we know pairs into electric gauge bosons that go beyond leading order. And at that order, when you do that, there are logarithms that enter, in fact, log squared that enter. That must be summed to all orders, and that is what SCET has been used for. And we can make use of those results. What I showed you here was the Sommerfeld enhancement factor for the inclusive annihilation rate. We can extend these results to partial annihilation rates. That is, for example, annihilation rate into monochromatic photons is one of particular importance. And in order to do that, we would need to use as inputs the results from these calculations that have summed the Sudakov logarithms in the annihilation rate. With those in hand, we can also do the Sommerfeld enhancement factors that take into account the resonance. Those calculations give us the short distance effects. The zero-range effective field theory gives us the long distance effects.
Let's get to the first round first.
It seems unitarity plays a role. So my question is, unitarity bound is an assumption, or in this framework, substitution of unitarity bound is an obvious thing?
Well, the unitarity bound is automatic if you do things properly. In our case, this is a log-log plot, and in this range here, well, this is the annihilation rate. But if you looked at the elastic scattering, this this region here is where there is elastic scattering saturated in the unitarity bound. This effective field theory framework automatically builds in unitarity, not only for the low energy interaction, but also the annihilation interactions. So we get saturation in the annihilation rate. We also find saturation at small velocities. All previous calculations, if extrapolated, would continue going on up and violate the unitarity bound. Our framework automatically builds in unitarity even for the annihilation contributions.
Okay, so I think we.
Okay, I think I may have more questions, but we can discuss later. Now I have two questions. One for just one. You mentioned the PP bar scattering for the EFT, right?
Yes.
How do you treat the PP bar annihilation? Because for the total cross section is around 200 nanobar, and annihilation constitutes around 80%. It's a very large portion, and involves many scales and quite complicated. And in Bohr potential, 9 megapotential, Paris potential, and also in the last year we construct the Cairo EFT. And I'm wondering, how do you treat the PP bar annihilation?
In this case, I was referring to work by Coleman Ravindal back in 1999. And what we needed from their work was the sum of all the photon exchange diagrams that occur in these bubble diagrams. And so all that we need their work for was the analytic expressions for the bubble with Coulomb summation and the vertex with Coulomb summation. And I'd have to go back and look at these papers to see what they said about annihilation. And I don't have any, it does not affect what we were doing.
Right.
And right is here just the elastic channel.
No annihilation.
I mean, the PP bar can go to pi pi and KK bar and anything, right?
Right.
And the pi 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 and so on, right? This cannot be treated in these diagrams. Maybe we discussed it, okay?
Yeah, I would expect that they were just doing the elastic scattering, but I don't know the details.
Yeah, okay, so you guys can have a more detailed discussion so that after break. Any other question?
Well, I will just leverage of the chairman is answered a simple question. So you cited the earlier work by material her collaborators. But your new calculation, there's something different or something that has missed?
But their approach will give you the correct results,
Yeah.
just with much more difficulty and complete numerically. And
Okay, so
our results can reproduce theirs we have analytic results that can reproduce the results of the difficult numerical calculations involving many length scales, and therefore it's hard to get the numerics down right. But the analytic results are nice and simple.
Okay, so now it's just provide some more detailed understanding of what is really going on.
In the specific case, when there are S-wave resonances near threshold.
Okay, so let's thank Eric. Welcome to the next talk. Talk is going to be given by Wenchen Zhang from IOP academia on recent results of drill-in experiments in exploring